Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 1. Bracketing Methods. Bisection Method. The bisection method is a numerical technique used to find the root of a continuous function. It is based on the intermediate value theorem, which states that for a continuous function f, x, defined in the open interval a, b, fa and fb have opposite signs, then there exists at least one root in the interval ab. The nonlinear equation is first cast as f(x) equals 0. Then, a suitable search interval containing a unique root is determined. Fa times fb less than 0 provides a criterion for bracketing a root in the interval ab. Notice that in the figure below, there exists a root in the interval ab. The endpoints of an increasing function have opposite signs. That is, fa times fb is negative. The endpoints of a decreasing function that intersects the x-axis have opposite signs. Similarly, fa times fb is negative. The search interval is then halved successively until the updated search interval becomes sufficiently narrow, smaller than a tolerance value. Consider the function f(x) plotted in the interval ab. First, we denote the interval endpoints with superscript 0. We observe that the function has a root in this interval and the signs of the function at the endpoints are opposite. Next, we find the midpoint x1 and evaluate the function at the midpoint, whose sign is clearly negative. This bisection leads to two intervals of equal size. Next, we need to determine in which interval the root lies. Here, we can visually observe how to narrow down the interval, but the computer cannot make a visual decision, and it will require specific instructions to decide on how to narrow down the interval. We will check to see if fb times fx1 is greater, equal, or less than 0. If fb times fx is less than 0, the root is in the right interval. If fb times fx is greater than 0, the root lies in the left interval. If fb times fx is 0, the midpoint is the root we are seeking. Since fb times fx1 is less than 0, the root lies on the right side interval. We repeat bisection procedure by updating the interval with superscript 1. The function at endpoints have opposite signs. The second estimate for the root is the midpoint of this interval, which creates two intervals of equal size. The second estimate moved closer to the root. fb times fx2 is negative. That means the root is in the right half. Before the next bisection, we update the interval with superscript 2. The third estimate is taken as the midpoint of the interval, creating two intervals of equal size. fb times fx is positive, meaning that the root is in the left half. So we narrow down the interval from the right side. So we update the right endpoint b with x3. This procedure of finding the midpoint and determining the interval having the root will continue until the convergence within a specified tolerance is achieved. A generalized procedure can be given as follows. We select an initial search interval. Then, we find the midpoint. If fa times fx is negative, or fb times fx is positive, the root is on the left side. We then set the estimate as the right endpoint. If fb times fx is negative, the root is on the right side. We then set the estimate as the left endpoint. If the magnitude of fx is 0 within a tolerance value, the root is set to the midpoint value. This procedure will lead to the true solution as the number of iterations goes to infinity. Recall that checking for equality of two floating point numbers as a equals b or a minus b equals 0 in programs is not a good practice. Hence, the root should be determined as whether the absolute value of the midpoint value of the function falls below a certain tolerance. Stopping or convergence criteria can be in terms of absolute error, relative error, or absolute value of the function at the midpoint. Or it can even be based on interval size. In the relative error criterion, a small number, the delta, is added to the denominator, preferably in the order of machine epsilon, to ensure convergence in case the root is 0 or very small. It is prudent to use two criteria to ensure accurate estimate. Before starting the iterations, one can estimate the number of bisections required to achieve a specified accuracy. A solution is said to be correct within n decimal places if the error is less than 0.5 times 10 to minus n. Substituting this value into equation 4.2 and solving for p, we obtain an expression for the minimum number of iterations as 2 based logarithm of interval width times 10 to the n. At the end of pth iteration step, the estimate is found as. Alternatively, we may use linear interpolation to improve the final estimate. The advantages of the bisection method are: the bisection method is simple and reliable. It converges to a solution under any circumstances, as long as there is a root within the starting search interval. The estimates for the root improve as the number of bisections increases. The error bound decreases by half with each bisection. On the other hand, the method has some disadvantages as well. Determining the starting search interval requires preliminary work to ensure that FA and FB have opposite signs. It cannot determine a multiple root since FA times FB is positive. It converges linearly with an average convergence rate of 0.5. For a large search interval, a large number of bisections is required to obtain an estimate with a reasonable degree of accuracy. An endpoint close to the true root does not ensure fast convergence. Imaginary roots cannot be determined. FA times FB less than 0 implies the existence of a root rather than its uniqueness. Consider the following nonlinear equation. Find its root, if it exists, in the interval between 1 and 2. The stopping criterion is based on the absolute value of the function being less than 10 to the power of minus 3. The endpoints of the interval are 1 and 2. We evaluate the function at x equals 1 and x equals 2. The midpoint is found as 1.5. Likewise, we evaluate the function for x equals 1.5. Now, to narrow down the search interval, we will check the sign of f2 times fx1. We observe that f2 times fx1 is positive, so we will keep the left interval or discard the right side. The search interval is updated as a1 equals 1 and b1 equals 1.5. We had already calculated f1 and f1.5 in the prior step, so there is no need to recalculate these quantities. The midpoint is 1.25, and the function takes the value of minus 1.898242. Next, we check the sign of f1.5 times fx2, which is negative, meaning that the root is in the left interval. So we update the endpoints of the search interval. We have the values of f1.25 and f1.5 from the prior step. The midpoint is calculated to be 1.375, and the function takes the value of minus 0.160,114. When this procedure is continued, the root converges to 1.384,399 after 12 bisections, with the convergence criterion based on the approach of the function value to 0. To summarize, starting search interval was from 1 to 2. and the epsilon was specified as 10 to the minus 3. The true root, accurate up to 9 decimal places, is computed to be 1,384,353,987. The estimate after 12 bisection is 1,384,399, which leads to the true absolute error of 4.50 times 10 to the power of minus 5. That is, better than the target value of 10 to the power minus 3. The improved estimate is obtained as 1,384,354 using the linear interpolation after the last step, which yields the true absolute error of 1.26 times 10 to the power of minus 8. The number of bisections required to reduce the interval width below the specified epsilon is found to be about 10. That is all for now. See you next time with another topic. Bye.